Now, just in relation to the assignment, as you know, the hand-up is on Sunday, I think. There is a README that I'll get you to fill out for it. I'll publish a template for that README either later on today or tomorrow. I don't think there's going to be a whole lot in it, so it shouldn't take you no more than 30 or 45 minutes to put it together, really. Also, you will need to make a video, YouTube video, essentially where you just step through demonstrating the workings of your API. You don't have to go showing me code and explaining code unless there's some particular aspect to your code that I didn't cover in the lectures. Other than that, it's not necessary. So it's really just demonstrating you can deploy your stack and then demonstrate the various endpoints. I guess that's how you would go about it. Either using Postman or whatever client you want to. And obviously you should really rehearse that to have a fairly smooth presentation. Just I'll pause for a second in case there are any questions in relation to the assignment. No? Okay. So I'll push on with the lecture in that case. And the slides for today are behind this card here. And I'll add some more slides to this deck next week. So it's 2 weeks ago now, but the last time I talked to you, I was explaining the evolution of the evolution of server-side software architecture, where we went from the monolithic architecture to the microservices architecture. And today, I suppose you could say we're sort of in the event-driven architecture phase. The idea with microservices, as you remember, was that you essentially broke up your overall application into mini applications. You could nearly refer to them as a collection of mini applications, although we refer to each mini application as a microservice. And the advantages of that, if you remember, was that meant that each microservice or mini application, it was independent of all the other microservices and could be evolved independently. Its internal implementation could be changed, its software stack could be upgraded, and that would not impact on the rest of the microservices that make up your overall application. At least that was the theory, and it made sense at the time. But what emerged after a few years was that there was still a lot of coupling between the individual microservices, so that, you know, when one microservice received a request to complete some sort of transaction, it had to communicate with another microservice or services. And so there was coupling or a dependency relationship between the microservices. And so in a way, we were back to where we were when we had the monolithic architecture. It now meant that you sometimes you couldn't really independently evolve one microservice. It was kind of dependent on the other microservices. And if you wanted to evolve a microservice, you had to check with the other microservices to ensure that they were still going to be able to work with your upgraded service. The advantage of microservices was that you could break up your overall software development team into smaller groups, where each group now had total responsibility and critically autonomy in how they wanted to evolve their microservice. So that was the theory, but as I said, it broke down a little bit because of this coupling problem. And so the solution to the, or a solution to the coupling problem is to try and decouple your microservices as much as possible. And the way we approach that is by using what's called a messaging broker between the services. So I think maybe the last slide that I showed you, I spoke to you last, was this slide here. Now there's a lot going on here, really, like, but here are our microservices, and they're not communicating with one another directly, but they are indirectly via this red box, which is our messaging broker. So so now we have the services publishing or writing messages to this message broker and other services reading from them. So now you had your individual microservices were more independent anyway than they were when there was tight coupling going on between them. So what I want to look at really for the remainder of this module is the red box. How do we implement that part of the infrastructure using AWS? So our title is AWS integration, as in you're integrating different parts of your application, different functional parts of your application. Now we're dropping down to the Lambda level. I did say to you that a microservice is typically larger than an individual Lambda. Microservices predates the Lambda invention, if you like, and you could regard Lambdas as just a further decomposition of an overall application into smaller units of functionality. First of all, we broke our monolith into microservices. Now we're breaking our microservices into Lambdas. So it's just another degree of decomposition, as I said. But your microservices stroke Lambdas, they presumably they need to communicate with each other. So how do we integrate them in a way that's not tightly coupled? And as I said, the mechanism is this messaging mechanism. So messaging will effectively give us this event-driven architecture. And there are a number of services that we could look at. The two that we will cover in this module is down at the bottom there, the SQS service and the SNS service, which you've probably heard of before from the DevOps, but maybe didn't really use that much. But there are other ones, as I said, like there's Event Bridge, there's something called step functions. They're just more advanced approaches towards this whole idea of integration and messaging. So we take SQS, well, why do we need these messaging services? I've kind of already made the argument, right? So we don't like synchronous communication between our microservices. Or even, if we were way back in the days of monolithic applications, quite often monolithic applications had to talk to one another as well, had to communicate with one another. So maybe one organization, that could be within an organization or inter-organization, maybe one organization's monolithic application, we would like it to be able to communicate with another organization's monolithic application. You can think of your classic kind of case of ordering goods from another organization or this kind of idea. So monolithic applications had to communicate as well, and that there was no simple means to achieving that. And it turns out that SQS and SNS were really aimed at that market originally. But we're talking about it in the context of microservices, or indeed in terms of Lambdas trying to communicate with, needing to communicate with one another. And this is where we don't like synchronous communication. So that's where that's the kind of problem that they solve. Also, the problem with synchronous communication is, and I've made this argument the last day, is it's problematic if there are certain spikes in the demands on a microservice, or if there are problems with the availability of a microservice temporarily, if the network goes down. If you've got synchronous communication, in other words, tight coupling between two microservices, service A and service B, and let's say service A is dependent on service B, as in it communicates with service B in order to complete a transaction. If there's a certain spike in the volume of requests coming into service A, it must scale up, obviously, and equally, service B must scale up in line with that. And that coordination of that scalability can be problematic. Also, if service B is just not accessible because the network is down or because it has temporarily crashed, then that means now service A can't complete its transaction. So they're all the reasons we don't like synchronous communication. So we prefer to decouple things, and there are a number of services on the AWS platform anyway that facilitate this, and I'm listing some of them here. What am I saying at the bottom? These techniques, result in various advantages, which I'll just move on from there. Really, they're obvious enough, I hope. So the first one we look at is SQS, and in very simple terms, the concepts that we need to, or the language that we kind of use when we're talking about SQS are publishers and consumers. So, sorry, now just 1 second. So a publisher, that could be, that's either a microservice or a Lambda. It's writing messages to a queue. This is our piece of intermediate infrastructure. And on the right, we've got a consumer, which is either another microservice or another Lambda or even a monolith. It's reading messages off the queue, but there's no synchronization going on between the I call it publisher there, I should have said producer really, because publisher has a slightly different meaning as we'll see later on. So we've got the producer of messages and we've got the consumer. But there's no synchronicity going on between your producer and consumer, as in the producer just simply puts the message on the queue, and then as far as it's concerned, it's done. It's not waiting around for any response back from the consumer. Equally, the consumer, the rate at which it consumes message doesn't have to be at the same rate that the producer is writing messages to the queue. So there's complete decoupling or independence between them. And down at the bottom, then I'm showing you, well, if we're just talking about Lambdas as our producers and consumers, this might be a simple little architecture where your requests are coming in from some sort of a client into API gateway. API gateway is triggering a Lambda. Now, this Lambda here, whatever processing of that request it needs to do, some of the processing needs to be done by this other Lambda over here. But rather than having direct communication, we're using an SQS queue as an intermediary. Like, the idea is that the processing that's done by this Lambda, while it's part of the overall processing of the request that came in over here, the client doesn't have to wait for the processing done by this Lambda to be completed. That may not be feasible in every case. So you have to pick and choose the cases where you can introduce messaging into your overall application. But let's supposing it does make sense in this case that whatever processing is done by this, the client doesn't need to wait for that processing to complete. All the client is interested in is, did this Lambda here get my request, and has it processed that request? Because there is synchronous communication here and synchronous communication here. Like a simple example might be, I upload a video and this maybe does some basic, it just records maybe into a database that the video has been uploaded, and it adds the video to this, or it puts a message into the queue indicating that a video has been uploaded. But it's this Lambda over here that maybe does some detailed processing of the video. But we don't want the client to be waiting around for that to happen. Okay, we will eventually have to communicate back to the client, telling it, you know, your video failed some validation criteria, but that response doesn't have to be in a synchronous way. Now, it turns out that SQS has been around. It's I think it is the first service that Amazon published to the community. So it predates microservices, it predates serverless. So really, they were actually aiming at a completely different environment. What they were trying to solve was the problem where you had monolithic applications that wanted to communicate with one another, but there was no simple solution to that. And that's where SQS came in. Amazon provided it for that particular purpose. Now, so it dates back to roughly 2006. I'm saying it's a fully managed. It's fully managed, and that's really a byword for saying that it's serverless. So there's no setting up of this SQS service from your point of view. It's distributed, and I'll explain a little bit about the distribution of the SQS service in a few slides. And it's used to decouple applications. That's okay. I'm saying it's unlimited, so it scales up automatically. There's an unlimited number of messages that you can put onto a queue. So the scaling is taken care of you, and that's typical of serverless. It has a certain amount of persistence of the messages, so there is a default retention of the messages for 4 days. It's not like a database, though. It won't hold on to them forever. So, but it will hold on to them for a period that you can define, but the default is 4 days. So, you know, if your consumers are, for whatever reason, not available to consume the messages on a queue, then the messages will remain in the queue for this period. Low latency, okay. You know, when you're writing messages, there's a pretty quick response back confirming that your message has been stored on the queue. There is a limit to the size of the message. So we're saying it's 256 kilobytes. Now there's a way you can work around that limitation, not by putting larger messages, but the workaround tends to be that you store, if you've got a very large message, you store the message, let's say, in a database. And the message that you put on the SQS queue then will just contain a reference to the database record that has the full detail of the message itself. I've forgotten what that pattern is called, but it's a very standard pattern. The caveats, we're told that we can have duplicate messages. So it is possible that the consumer will receive the same message more than once. It's very rare, but Amazon say that it is a possibility. That now has implications for you, the developer of the consumer functionality. You've got to make sure that your functionality deals with that scenario, that it doesn't sort of process the same message twice, if you like. Second caveat is that the second caveat is a consequence of the first one, really. Your consumer has to be idempotent. That really means that it can handle the possibility of processing the same message more than once. I won't get into the idempotency, how you go about that, but just need to be aware, be aware of it. Also, Amazon say that there's no guarantee that the ordering of the messages, so the order in which messages are written to the queue by the producer, the consumer won't necessarily receive them in that same order. In many cases, that's not a problem. If it is a problem, then you can configure your queue such that the ordering of the messages is maintained. It does have implications though on on latency, so you try and avoid that if you can. And in the majority of cases, the ordering of messages isn't actually important. So as I said, we have two actors in this, using this SQS queue. We've got the producers. The producer writes messages to the queue using the SDK, the SQS SDK, and we'll see that a little bit later on. Messages are persisted. I've already made that point. Well, they're persisted to the queue. I'm saying there until a consumer deletes it. So messages, the consumer is responsible for deleting messages off of the queue, as well as reading the messages. The consumer must explicitly delete the messages from the queue. Otherwise, they will remain there. They'll remain there either until the message, its TTL, its time to live, expires. You can set a TTL property of a message when you write it to the queue, and that can be less than the default persistence of 4 days. So that's straightforward enough, I think. If I just go back for 1 second, remember now I said SQS dates back to around 2006, so it's way back in the monolith days, but you can have more than one consumer for a particular queue. You can have more than one producer as well, but on the consumer side, and particularly, I just want to make one point. It's not really relevant that much anymore, but it would have been relevant back in the 2006, that kind of period. So if you've got more than one consumer associated with a queue, then only one of the consumers will get to see a particular message. If that's not what you want, if you want all of the consumers to see all of the messages, then you can't use SQS. You've got to use another service, essentially SNS. But the point I'm trying to make is with SQS, if you've got more than one consumer, once one consumer reads a message and processes that message and deletes it, then obviously the other consumers won't see it. That's not a bug, that's just the way it's designed. On the consumer side, now the way the consumer works is it's a poller, right? It essentially polls the SQS service. So it's repeated, it's periodically checking with the SQS service. Are there any messages on the queue for me? And SQS will respond accordingly. Also, I'm saying that what the consumer receives is not an individual message. It receives a batch of messages. Even if there is only one message, that will be presented in the form of a batch, albeit a batch of one. But and you need to be aware of that when you're processing the response that you get back from a polling request. There seems to be a limit of if there's quite a number of messages in our queue when the consumer polls it, like maybe hundreds, then the batch size is 10. So you'll get 10 messages. The consumer processes those 10 messages, explicitly deletes them, polls again, gets the next 10, and so on and so forth. It won't get 100 messages in a batch. There's an upper limit. Not sure if you can configure that, but possibly. Process the messages, it processes the messages, that's okay. Processing could be anything really, maybe validating the messages and storing some data in a database as part of the processing or whatever. And as I've already said, it then has to delete the message, again, using the SDK. So it has to tell the SQS service to explicitly delete a message from the queue. Security, the messages are encrypted when they're stored in our queue. AWS takes care of that. And also the communication between your producer and the queue, and between the consumer and the queue, that communication line, which is over the network, obviously, is encrypted by SQS as well. So you've got, as we say, you've got in-flight encryption and at-rest encryption automatically built in. I'm saying in terms of access control, clearly you can use define IAM policies, which determines how much access a microservice stroke Lambda has on a queue. That goes without saying, I guess. Also, from the SQS side, you can associate an access policy, which controls whether your queue is accessible to other AWS account users. And so, in other words, is it cross-account accessible, or can other services, other than, let's say, Lambda, can other services access your queue? And we will find that in many cases, it's other services rather than just Lambda that will be either writing to a queue or reading from a queue. But in order for those other services like S3 and SNS, I'm mentioning two of them there, for those services to be able to access a particular queue, you've got to configure the SQS access policy to allow that. But as we know, with the CDK, it takes care of a lot of that messy stuff for us. Simple example. In this example, I'm going to create an SQS queue. I'm going to have a Lambda that reads messages off of that queue. Well, my Lambda is over here. So I said the consumer, so this is my consumer, and I said the consumer polls SQS for asking it, are there any messages on the queue? Now, when it's a Lambda, when your consumer is a Lambda function, it's actually the Lambda service that takes care of the polling for you. So it's the service is now polling the queue, checking for messages. And if there are messages, it receives the messages, and then it sends them, or it invokes your Lambda function with a batch of messages that it has received. Okay, so sorry, just to complete the picture, if your Lambda successfully processes the batch, as in it doesn't crash and it doesn't time out, then the Lambda service will take care of instructing SQS to delete the messages. So you do not have to put code in your Lambda function concerned with deleting messages from a queue. The Lambda service does that, which is kind of nice, really. Otherwise, it just gets, we just have to keep remembering to delete messages from the queue. Whereas if we were back in the monolith days, and the monolith could be an application running inside an EC2 instance, or indeed an application running on an on-premise server, nothing to do with EC2. But let's say if it was an application running inside an EC2 instance, then you would actually have to would have to write the code as part of your application that handled deleting messages from the queue. You had to do everything, whereas now the Lambda service does some of that for you. So that's what we want to. This is a very simple little example that we want to set up for ourselves. And so I can have made this point: the Lambda service polls the queue For messages and calls a Lambda function synchronously, that's okay. If the function processes the batch without a failure, then it deletes it. That's okay. I've made that point as well. If however the Lambda function on the extreme right there doesn't complete the processing, either because we haven't given the Lambda service enough RAM memory to do its processing, or if one of the messages causes my Lambda to throw an exception. In either of those two cases, the messages, the Lambda service itself will not, obviously enough, I suppose, it will not delete the messages from the queue. It's going to leave them there, which means that the Lambda service will get the same batch of messages a second time and pass them on to your Lambda function a second time for processing. So, you know, we have to deal with that scenario, but that's how it would actually work in reality. And this goes back to this idempotency idea. So it's possible that your Lambda function could receive the same messages more than once for processing. In terms of code, how do we set this up from a CDK point of view? Pretty straightforward. You just create a queue. You attach the queue to the stack. You give the queue some sort of unique text name. Now, there's lots of configuration that you can do of the queue, but we don't need to do any of it for this example anyway. We have our Lambda function here. This is the Lambda that's going to process messages. You know, there's nothing unusual about it. We don't have to pass a reference to the SQSQ to our Lambda service as an environment variable because, sorry, we don't have to pass a reference to the SQSQ to our Lambda instance because the Lambda service is taking care of interacting with SQS, and the Lambda service just calls our Lambda function with a batch of messages. So as the event, if you like, of the Lambda function. So it doesn't have to talk to it directly in this particular example anyway. This is how we hook the two up really. We do obviously have to, I suppose, tell the Lambda service tell the Lambda service that we want messages being put onto this queue here as being the trigger for invoking my Lambda function. And so it's just a two-step thing, right? It looks like, first of all, I have to create an SQS event source, associate that with my queue, and then add that event source as an event source for my Lambda function. So that might be slightly counterintuitive to what I'm kind of saying to you, that clearly we are hooking up our Lambda function with the queue here, but how this actually gets implemented is, as I was talking about earlier on, it's really the Lambda service takes care of talking to the queue for you, and the Lambda service passes batches of message to your Lambda function. But you do have to tell the Lambda service, I guess, about that, and that's what the effect of these two lines of code is. Right, that's that. My Lambda function, this is my consumer in this case. And all we can get from this is, okay, our event in this case, the event is going to be a batch of messages from my queue. And I'm doing console.log of the event here, and I'll show you what that looks like on the next screen. But the important part maybe is this for loop here. This is confirming the point that I've made on a number of occasions now, that what you actually get is always a batch of messages. Quite often there's only one message in that batch. but we do have to iterate over the batch. And so it looks like the batch of messages is contained in a property called records of the actual event object itself. And I'm just consoling the message. So nothing too exciting there really, other than the need for that for loop or some sort of iteration. This is how I might call. So I've just decided for simplicity to use the AWS CLI to publish or to produce messages and publish them or write them to the queue. So this is how you would use the CLI to do that. This is just a reference to the queue. The queue will have a URL when it's created. So that looks like that was the URL of the queue when I was playing with this. And where's my message? My message body is just a piece of text. And so when I executed that from my terminal, and then if I go into CloudWatch logs and see what does it get for, let's say, this console.log, what does that produce? Then here's what, so this is the event, the full event that the AWS service now passes to my Lambda function, my Lambda handler. And as the code has kind of indicated, here's the overall event. It starts up here and finishes somewhere else. And the main property is this records property, which is in an array, as we can see. And each object in this array is one message from the queue. The message has lots of properties. Interestingly, each message has an ID, a unique identifier, and so on. And if we dig down into it, inside the message, there's a body property, and the body property has the actual message itself, if you like. So all the other properties are added to a message by the SQS service itself. And do we access body? If I go back, we can see we're accessing the body here of a particular record, it calls it, but it's one message from the queue. So that's straightforward enough. I'm not going to do a manual demonstration of it. If we want to send JSON, which is 99% of the time, if we want to send JSON data as our message, then let's supposing this is the JSON structure that I want to pass or that I want to write to my queue. The way I do it just using the AWS CLI is I have to add on this the message body. Again, I just have to use this file protocol to refer to the actual JSON file. So this is a reference to this file up here, I guess. And the point I'm trying to get across from this slide, though, is that we see now here's the body of the message, but my JSON has been stringified. So when you write a message onto a queue, the SQS service will automatically stringify that message. And so that's what we're seeing here. It's a stringified JSON object. But from the consumer's point of view, it obviously needs to destringify it or parse it. So if I now look at my updated Lambda handler, you can see that's what I'm doing here. I am parsing my body, and you would do that automatically, even if it wasn't JSON. If it was just an ordinary text string, you could, maybe you don't actually have to parse it. Maybe you do have to know that it is JSON. Okay, so that's the only point I'm trying to get across from this slide and the previous one. And this parsing is something that happens quite a lot with all of the messaging services that AWS provides, and you just need to be aware of it. Okay, I haven't demonstrated anything though, but hopefully the example was simple enough that it doesn't need a demonstration. There are a couple of points I want to get across from this slide, and I said when I talked about SQS initially, I said that it was a distributed service, or queues were stored or persisted in a distributed way. And so it turns out that when you create a queue, there are actually multiple copies of that queue stored on various servers scattered around an AZ zone, or sorry, scattered around a region. And so that's what that's the first point I'm trying to get across on this slide. So we're showing Maria a queue, and it has a number of messages in it titled A, B, C, D. But those messages are actually persisted onto multiple servers scattered across a particular AWS region. And obviously scattered across the AZ zones within that region. Now, every server does not, if you kind of study it, every server does not have a copy of every message. It only has some of the messages, and AWS SQS takes care of how it distributes copies of a message using some sort of algorithm. That's the second point. The third point is, when a consumer, and let's suppose we've got a number of consumers over here, when a consumer asks SWS for messages from a queue, then what SQS does is it samples a subset of these servers, not all of them. And again, it's an algorithm as to what subset it samples at any particular point in time. And so if it only samples a subset, that means that there may be a message that is not stored on the subset that it chooses. And that's why AWS does not guarantee that the order in which you receive the messages is the order in which they were written. So, a consumer, we know the consumer is constantly polling SQS. So it polls it for some messages. SQS takes a subset of the servers and sees, are there any messages on that particular queue? And if there are, from the subset of servers that it has chosen, then it takes those messages and sends them to the consumer. Same consumer will come back for a second polling subsequently. The second polling request, in this case, the SQS service will again randomly select a subset of the servers. Well, not completely random, but using some algorithm. But in the second polling case, it would bring in some of the servers that weren't included in the first polling request. So eventually, the consumer will get all of the messages, but there's no guarantee of the ordering. The other reason, obviously, why SQS approaches the storing of a queue in this way, it has got to do with availability. So if any particular server or a set of servers within an AZ zone go down, then we know at least there are other servers on other AZ zones that will have some, possibly all of the messages for that particular queue. So when you create a queue, your queue is actually, there are multiple copies of it distributed across the servers that make up the SQS service for a particular region. The bullet points when your consumer queue. I think I've probably explained what this bullet point is saying. So SQS is resilient. That's a little bit like the way DynamoDB worked as well, if you remember. In terms of the consumer, and when the consumer is a Lambda, then the Lambda service takes care of scaling up copies of your Lambda function instance, depending on how much how many messages are being written to the queue. So the higher the volume of messages, obviously, the Lambda service will start scaling up copies of your Lambda instance to deal with that. And the specifics of it, I'm talking a little bit about down here. I'm saying the Lambda polls the queue as we know. As it waits for messages to arrive, the Lambda consumers, well, the Lambda instance consumers the Lambda consumes messages in batches. That's okay. Oh yeah. I think by default, what Lambda does is it creates 5 instances of your Lambda function as a kind of a lower bound in terms of concurrency and scalability. And then it will scale up from that 5 instances depending on the volume of messages that it gets back from a polling request. And I'm talking about the rate at which it scales up here. So that's kind of, you don't have any control over that to a degree. It's just built into the Lambda service as to how it scales up and down. Now, it does turn out that we can control the number of default copies of your Lambda function that are created. Its default is 5. It will just nearly always create 5 copies of your Lambda. That's before it polls the queue for any messages. It just assumes that it's going to need a minimum of 5. Now, depending on how much activity there is happening on the various AWS servers, though, but you can actually set it at a lower, or you can set it at a higher value from a CDK point of view. So the scaling, again, is taken care of out from the consumer side. The scaling is taken care of by the Lambda service for you. And the scaling of the actual SQS queue is taken care of by SQS automatically from the previous slide. Let's look at another little example. So in this case, what I have is I've decided to use just a Lambda function to generate messages, and notionally it's generating orders. And it talks to the SQS service. It uses the SQS SDK, and it talks to the service in order to write messages to the queue. And on the other side, I've got a consumer, which is a Lambda as well. So that's fairly, again, fairly straightforward, I guess. This is really the only purpose of this Lambda here is it's kind of a test harness, if you like. It's driving, rather than using the AWS CLI, it's driving the generation of the messages for me. And what am I showing you down here? Okay. Maybe what I'll do is flip over to VS Code at this stage, maybe. So that's the architecture, if you like, that we want to implement. Now, I've already deployed it, but if I just step through it a little bit. So here's my stack file. And I'm creating my queue. Nothing unusual there. Here's the Lambda that will be processing messages. It's fairly standard. Here's the Lambda that's going to be generating the messages. Nothing unusual there either. Here's where I'm connecting up my consuming Lambda with the queue. Is that what I'm doing there? Yeah, that's essentially what I'm doing. So I'm creating the SQS event source, and then I'm adding that event source to my processing Lambda. Now, I've commented out this line for the moment, and I'll come back to it. This essentially is how you control how many concurrent instances of your Lambda are you allowing the Lambda service to fire up on your behalf? This property here is controlling how frequently we want the Lambda service to poll SQS for messages. So I'm saying it's every 10 seconds. I think the default is every second. And again, that becomes a tuning thing that you work out based on the rate at which you think messages will be written to the queue. But I've just decided I'm going to set it to 10 seconds. Now, the Lambda that's writing messages obviously has to have the permissions to do that, and that's what this is doing. So that's very much like the way we give a Lambda function permission to write to a database. So there's the nice convenient function, but that generates the IAM policy behind the scenes as before. And I'm just publishing, or I'm outputting the name of the Lambda that writes messages, because I'm going to be triggering that from the command line. If I look at the Lambdas themselves, this is the one that generates and writes messages to the queue. So what I've done, just as a convenience, is I've created an array. Well, first of all, I have a type called order. Where is that? That's inside here. That's my order structure, and it's orders that I'm going to be writing as messages onto my queue. So an order has a customer name, customer address, and items, which is an array of strings, just for simplicity's sake. So inside in the Lambda that's generating these orders and writing to the queue, what I've done is I've just created an array of orders. Now, we don't need to worry about, I do have a bad orders type as well, which I don't need actually right now, so we can kind of ignore that. So you can regard this here now as being an array of order objects, yeah? And I put 6 in there. I've commented out this one because this is actually turns out to be a bad order structure. And we'll talk about how we deal with those in a while, but it's not part of this demo for now. And here's my handler. And what does the handler do? What the handler will be doing is writing the messages. Now, a message has to have a predefined structure to it, and the structure is defined by this type, which comes from the SQS SDK. And this structure has a number of optional fields, but the mandatory fields are each message has to have an ID property, and each message has to have a message body property. And so I'm just simply mapping over, you can see what I'm doing is I'm mapping over the array of orders that I have up here. I'm mapping over them, and I'm producing an object of this type for each order. I'm generating an ID, a unique ID for each message, and I'm just using a third-party library called the V4 library. So that'll just randomly generate a UUID essentially for me. Okay, and of course I am stringifying the body. Actually, I didn't think I had to do that now, but it looks like I do have to do that. It's not SQS that does it. That's probably because if I just do a Command K, Command I. Okay, that's because the type is string. So I do actually have to do the stringifying of the message, which means that the consumer on the other side has to parse it. Now, in this particular case, I'm sending these messages using, I'm using the client here. I'm using the client, SQS client from the SQS SDK. And that client is modeled in the same way as our DynamoDB client, where we have commands, we generate command objects, and we send a command object from the client, and that really gets whittled down to the appropriate HTTP request from my Lambda function to the SQS service. So in my case, I'm using the send message batch command, but there's also a send message command. In most cases, you would only be sending one message, whereas I'm sending a group of messages, and the batch command is specifically for that scenario. So that's the only reason I'm sending them as a batch. You don't have to always write messages to a queue. You don't have to write them as a batch. You would write them individually. Nevertheless, so I've what am I doing? I'm first of all just constructing the structure that's required by this send message batch class. So I'm specifying the queue, which is passed in as an environment variable. I didn't show you that, but let me just quickly flip back to that. Is that an environment variable? Yeah, you can see that I'm just passing it in as an environment variable. So I'm specifying the queue that I want to send my batch of messages to, and I'm telling it where the batch is. And the batch is referring to this structure here. And then I send it, send this command to my client, and that writes the messages. All I'm showing you down here is actually how you would, if you want to write a single message, this code demonstrates that. I just commented it out. I don't need it, but you can look at that later on yourselves. So that's the generator. The Lambda that's processing the messages has nothing terribly new in it, I don't think. Let's see. No, okay, so it just has the for loop as before. It's iterating over the batch of messages that it receives. Now, I am doing validation here, which isn't actually important right now, but I'm validating the body of each message to make sure that it's a valid order object, if you like. And I'm using that the AJV library to do that, which we've seen before. So, okay, that's new, but that's not terribly, we're familiar with it from before. And I'm throwing an exception if it finds an invalid order. Now that is significant, but not now, not right now. If it doesn't find any problem with it, then it just processes the order. And I am console logging the message itself for debugging purposes. Okay, so what I need to do in order to trigger this, I have already deployed it. And so we know now, let's just trigger the Lambda that generates the messages. And my command, which I've just stored here for convenience. So I'm just triggering a Lambda. So it's going to be this AWS Lambda invoke. Copy that. Now the stack that I had there is actually outputting the name of the Lambda that generates the messages, which is here. I'll just tag that on there. And I do have to also provide a file for storing the response, which is just an AWS CLI thing. So I'm just going to take this part. Just check it now. So, okay, let's go. Now, if we flip over to CloudWatch logs and see what happened there. Okay, so I'm in CloudWatch logs. I'll just do a refresh. Okay, so I've got the logs coming from the generating Lambda and the logs coming from the processing Lambda. And it's the processing one that I'm interested in. So if we drill down into that, and I've got 1, 2, 3, 4 streams. 1, 2, 3, 4. Now, I said in terms of scaling that Lambda by default creates 5 instances of your consumer, even before it kind of receives, even before it polls at all. Now it's within that range anyway. Like it seems in this particular case that it created 4 concurrent instances of my Lambda. If I just go back to the slides, when I did this beforehand, if I go on to this one here, you can see actually it has 1, 2, 3, 4, 5 streams associated with my consuming Lambda. And there's a stream per instance of my Lambda. So when I played with it, whenever I ran it and took a screenshot, it did actually create 5 concurrent instances, whereas in this case, it has only created 4. And that really probably is just down to, the amount of activity that's happening on the AWS platform. And so if we look at each of these streams, so some of these streams will indicate that the batch was of size 1, whereas others will have more than 1. And so if we just step through them one by one, did I click on that? Okay, here we go. Now, I can kind of tell from the console logs that this one received a batch of 2. I know from the console logs, this one here relates to the order for user 1. This one was for, sorry, now am I right about that? Oh no, sorry, it only got its batch size was only 1. It only got 1 message in its batch for user 1. Okay, so that Lambda instance only received a batch size of 1. And if we keep going, click the second one, it also only received a batch size of 1. So it's pretty inefficient when you think about it. And in terms of ordering, this is processing the 5th order. I gave the orders, the usernames were user 1, user 2, all the way up to user 6. So that's where I'm getting that from. So that just also got a batch size of 1. Sorry, I'm just rechecking now. Is that right? Yeah. Eventually we'll get to one that has, hopefully. Where are we here? Another batch size of 1. Hopefully this isn't all going to collapse around me now if I check the last one. It's not adding up, is it? Batch size of 1 as well. So that's customer 3. Let's see what went wrong. Do a manual refresh again. And now about this, am I misreading? Oh, hang on, misreading it. Yeah, you can see here now, this one has a batch size of 3. User 1, user 2, and user 6. Okay, so that adds up. So that Lambda instance got a batch size of 3, and the other 3 Lambda instances received a batch size of 1, which gives us a total of 6 messages, which was a number in my orders array there that I showed you. Now, okay. If I wanted to, if I knew, look, I don't really need, in this case, 4 concurrent instances of my Lambda, maybe 2 concurrent instances would be sufficient to have available for consuming the messages, then I can tell that to the Lambda service by means of a configuration. And if I go back to my stack, and it's this setting here. So what this is saying, as I mentioned a while ago, this is telling the Lambda service, never have more than 2 concurrent instances of my consuming Lambda. So if I save that and now redeploy, and while that's deploying, I'm going to go back to CloudWatch. Something that I do is I like kind of cleaning up CloudWatch logs fairly regularly, because there's a danger that you might be looking at slightly older logs, certainly when you're in debug mode. So I'm just going to delete these. And I have, my stack has redeployed. And let's send another batch of 6 messages to my queue. Now, what I'm predicting in this case is that there will only be 2 streams in my CloudWatch logs, reflecting the fact that there were 2 concurrent instances of my Lambda that were fired up to process the messages. So let's see if it's going to make a liar of me. So yeah, it looks like that there are only 2 streams. So let's see, how did it split the batch of or the 6 orders? How did it split that up into 2 batches? So this Lambda is processing user 5, is it? User 5 and user 1 and user 2. sorry, yeah, user 6. A little bit for myself. User 6, user 1, user 2. That's a nice illustration of the ordering issue that I mentioned. There's no guarantee that the messages will be in the right order, and that's kind of confirmed by what you're seeing on the screen there. So it sent 3 orders to the Lambda that we're just looking at there. 1, 3, and 6 was it, we said. And if we look at the stream for the other Lambda, it got 2 and 6. I'm misreading something. 1, 2, and 6. Did I click the same one? Two. Adding up from it. Okay, 5, 3, 4. Okay, that makes sense. Right. So Lambda will do the scaling automatically for us. We control it. It's what we're getting there. We're also getting the ordering of the messages confirmed for us. Right. So let's move on. Go back to our slides. The log streams, that's okay, I think. Oh yeah, that's go on from there. When our Lambda service holds SQS for messages and it gets a batch of them, and Lambda then subdivides that batch as we know. But the messages that are sent to the Lambda service by SQS, those messages are still physically in our queue. But clearly, if there was another microservice, let's say, another component that was reading messages off of the queue, and we didn't want that other microservice reading the same messages that were sent to my Lambda, then how do we prevent that from happening? And the answer is it's kind of built into SQS. Messages automatically have what's called a visibility timeout period. And this is what we're trying to explain by this diagram here. So when the SQS service gives a batch of messages to a consumer, then it starts a timer for that batch of messages called the visibility timer. And you can control what the duration of that is. The default, I think, is 30 seconds. And the purpose of that visibility timer is to prevent any other consumer which may poll the SQS service in the meantime, asking it for messages. It prevents SQS from passing those same messages to that second consumer for that visibility timeout period. When the visibility timeout period expires, then those messages, if they're still there in the queue, they will be available to any consumer that requests messages from SQS. Now, hopefully what happens during this visibility timeout period is, in other words, what happens while a batch of messages are not visible to other consumers. Hopefully what happens is the consumer that actually received the messages processes them successfully and tells SQS to delete them from the queue. So they're deleted in that case. And anyway, when another consumer comes along and asks SQS for, are there any messages in the queue? Well, the messages just won't be there. The ones that have been processed won't be there. On the other hand, if the consumer that did receive the batch of messages was not able to process them successfully within the timeout period, or indeed if it, through an exception while it was processing them, which kind of has the same end result, that they haven't been successfully processed and deleted, then those messages are now visible again after the timeout period and available to whatever consumer comes along and happens to poll SQS for the messages. So that's how SQS avoids multiple consumers receiving the same messages and processing the same messages, because the way we want SQS to work is we only want one consumer to process a particular message on the SQS queue. If you want multiple consumers to do it, then don't use SQS, as we'll see. There's an alternative. So if I just quickly allow a message, after a message is polled by consumer, and the consumer can be anything, green EC2 instance, could be the Lambda service, it becomes invisible. The default visibility period is 30 seconds. So that means the consumer has 30 seconds. I know from reading, the consumer has 30 seconds to process the message and delete it. It has to do it all within that 30 seconds. And so, you know, if messages are quite, in terms of the processing time required on a message, you have to, in real life, you'd have to compute that, and it may be longer than 30 seconds. So you would change the visibility period accordingly. Okay. We won't really play around with visibility timeouts in this module anyway. Now, the scenario though, where a batch of messages are given to a consumer and for whatever reason, the consumer throws an exception as it's processing one of the messages for legitimate reasons. In our case, it will be an invalid order. In that case, when it throws the exception, what happens automatically is the batch of messages that the Lambda, let's call it, the batch of messages that the Lambda is processing, the entire batch now, is actually put back into the queue, and the visibility timeout period expires, and they're now still available to be processed. So that's the default behavior. And so that would mean really that if you've got a faulty message, that faulty message and the messages that it is batched with, they're constantly being put back into the queue and being reprocessed. Now, presumably, you don't want that to happen. If they're put back into the queue because the consumer wasn't able to process them in time, that's okay. But if it's because there's something faulty in the message in terms of its structure or whatever, and the consumer throws an exception, then really in that situation, you'd like the faulty message to be removed from the queue. And this is what the role of the dead letter queue is. A dead letter queue is a second queue that you associate with your main queue, and you're essentially telling the SQS service to put faulty batches into this dead letter queue. And typically then you would have another consumer which is responsible for processing this dead letter queue. So this is what we've got here. We've got our, what I'm calling my kind of regular queue, which is receiving orders in my case. I've got my consumer here. The consumer, for whatever reason, throws an exception. Now, you have to decide whether you want to allow the faulty message to be reprocessed, or whether you want it to be put into this dead letter queue, and when do you want it to be put into the dead letter queue? Do you give it more than one? Do you give the consumer more than one opportunity to try and reprocess the faulty message? That may make sense in some scenarios, it may not in other scenarios. But you connect up these two queues and you nominate this as being the DL queue for this. And then doing that, then that's essentially telling SQS where it should put faulty messages from the main queue. So if the consumer does not process a message within the visibility period, and by that I mean it either throws an exception or it wasn't able to process it, the consumer wasn't able to process it within its own the confines of its own computing power. Either way, the message has caused problems, let's say. Then not only that message, but the batch associated with that message, that batch is put back into the main queue. However, we can set a threshold for how many times the message is put back into the main queue. And in the case of the Lambda, when it's a Lambda consumer, this property here, maximum receives, is the number of times that you're saying a faulty batch can be put back into the main queue. Right. And this obviously happens, the reason this DLQ concept exists at all is because, it would be not an irregular occurrence that faulty messages do get into your main queue, and they have to be handled in some sort of structured way. So what we're going to do is we're going to add a DL queue, or associate a dead letter queue with our orders queue, and we're going to have a Lambda that processes the messages that go into this DL queue. Now, all our Lambda does is it just console logs stuff, but it's making this connection here is what I want to demonstrate. And also I want to demonstrate how you tell SQS how many times a faulty batch can be reinserted into this queue before eventually they get kicked off and put onto this dead letter queue. Let's see, I should have done this a few moments ago. I want to destroy that stack. So while that stack is being destroyed, if I look at this example, and if we look at the stack file first, so we've got, this is the queue that we had before, sorry now. It's the queue we had before. This is the dead letter queue, but it's just a regular queue. Oops, sorry. It's just a regular queue. This is our main queue, as I'm calling it. And this is how we're connecting up the first queue as being the dead letter queue for this main queue. That's what we're doing here. This is how we control how many times a faulty batch is allowed to be reinserted into my main queue. And I'm saying really, once a faulty batch has been found, then it should be put into the dead letter queue straight away. So there's only one. This has been set to one. Can only particular faulty batch can only be processed once, if you like. This is how you would control the visibility timeout for a queue, but we're not playing with that really today. And I've still got the same lambdas. I've got the lambda that's processing the entries in for my main queue. I've got the lambda that's generating the orders, and this is my lambda for processing the messages that go into my dead letter queue. And really all that lambda is doing is just console logging stuff. I'm setting up the what am I doing here? I'm setting up the main queue. I'm adding it as an event source for my main processor, my main consumer. So that's the same as before. I am setting up my new lambda as a processor for the messages that go into my dead letter queue. And we've seen that before. And that's it really. So the only changes are I've got a second queue and I've connected that second queue as being the dead letter queue for my main queue. And I've got a lambda that's processing the entries that go into the dead letter queue. Now, in order to trigger something going into the dead letter queue, if I go back to the lambda that's generating the messages for me, and if you look at this order here, this is going to be this order is an invalid order because it doesn't have a customer address property. Now the other orders are okay, and I should have mentioned this, you probably picked it up. So my orders, the user, the customer name, I've kind of given things something meaningful that makes sense when I look at the console log. So I've got user 1, user 2, user 3, user X is for the faulty one, user 4, 5, and 6. Okay, so let me just check one other thing. Okay, so I've set the concurrency level for my main queue processor to 2. Okay, I'm just going to leave it at that actually. So it's so my stack has deployed hopefully. Yeah, and is it? Sorry, it didn't deploy it. I need to deploy it now. We've done that while I was talking. Let's see. Again, I'll clean up the CloudWatch logs so I have a cleaner picture. Now, because I have set concurrency level to 2 for the Lambda that's processing the messages on the main queue. And I have a total of 7 orders. Then that 7 is going to be split up, whatever, 4 and 3, or could be 2 and 5. We don't really know. It's up to the Lambda service as to how it splits them up. But whichever instance of my main processor receives the batch containing the faulty order, that entire batch is going to be put into the dead letter queue, which means that the dead letter queue is going to have the faulty order and some valid orders that would happen to be part of the batch that contained the faulty one. And so clearly the Lambda, this Lambda here, which is processing the dead letter queue, in real life, what it should do is the orders that it finds that are actually okay, it should put them back into this queue to be processed. And the one that is actually faulty, well, it depends on what you want the Lambda to do with faulty ones. Send a message, send an email to whoever, or that doesn't really matter. We needn't get into that detail. But I'm just saying that because of the way I've set this up, there will be valid orders that go into this queue, which really should be put back into the main queue for proper processing. That's just how it turns out for this particular scenario. Okay, so it has deployed, and if I trigger my Lambda that generates the messages, now it's a different Lambda in this case because it's a completely different stack. So I need to doctor this a little bit. Here's my new function name. Let's do it this way. So what I'm getting wrong there now, but let's see. Okay. this is where on it. So there's only one, looks like there's only one log stream. So I should be getting 3 log streams because I have 3 lambdas. And the reason there's only one is because I set the polling frequency of both of my lambdas to 10 seconds. And so by the time I refreshed the screen and got the response back from this CloudWatch console, neither of the 2 lambdas that are processing messages in the queues, neither of them have polled SQS for messages in that 10-second period. But if I do a refresh now again, then I have all my 3 streams that I expected. So if we look at the processing one first, which is this one. I set its concurrency level to 2. So one of these 2 streams here now received the invalid order, and we know the invalid one, it was for user X. So we need to look for user X. There it is there. There's user X. So this batch consisting of user X order and the user 4 order, that batch would have been put into the dead letter queue. And so when I look at the console log from the Lambda that's processing the dead letter queue, I should get confirmation that it is actually reading those 2 orders. Whereas, just to complete the picture, the other Lambda, which is this one, which should I pick, the first one or the second one? This one receives the 4 or 5 actually. It receives 5 orders and they're all valid ones. Okay, so it was an unusual splitting up there of 5 and 2. It didn't split it to 4 and 3 or anything like that. But if we now look at the other stream, which is this one, and you see it actually, oh, okay. I think we got lucky in this case. Well, no, okay. It created 2 instances of the Lambda that's processing the dead letter queue because I set the concurrency level to 2, even though there were only 2 messages. So each one of these, one of them has will be processing the user 4 order, and the other one will be processing the user X order. So which is which? That one is processing the user X order, and hopefully the other one is processing the user 4 one. And indeed it is processing the user 4 one. So in this particular case, this instance of the Lambda should put that back into the what I'm calling the main queue. Okay, I will pause for questions, but I'm not sure if you're going to fire anything at me. You certainly need to study this, and I'll provide the code that I'm demonstrating here. I will provide it to you to study, because the bad news is this kind of comes into the second assignment. It's all about event-driven architecture, but that's for another day. It's just, I think I've gotten to the end. Yeah, all I'm showing you here are just screenshots from the code, which I've talked my way through. Yeah, that's just the Lambda that's processing the DLQ, and it's just doing console logging. And that's just explaining what's happening behind the scenes, which hopefully I've talked my way through, so I don't need to read through this. And they're just some screenshots from the console logs. I don't need to talk through those either because I've actually shown you a live demonstration of it. Okay, so that's SQS, and it's very much what we would call a point-to-point communication medium, as in typically anyway, even though you can have multiple consumers associated with the same queue, and again, the caveat is though that only one of those consumers will get to see any particular message. You cannot have each consumer seeing the same message. But typically there, in modern day usage of SQS, there is only one consumer, and typically it is a Lambda. So it's a kind of scenario that I've been demonstrating to you. There could be multiple consumers or multiple producers of messages, but that tends to be only one as well. So that's why we often refer to SQS as a point-to-point integration mechanism, as in there's only one producer and one consumer, but they're not communicating directly. They're going via the queue. Right. This week's lab, whether you've started it or not, this week's lab is using SQS. And so if you haven't started it, then it would be good now to play around with it. Although in the lab, I am using an S3 bucket as a mechanism for sending messages into an SQS queue. So I did say that the producer can be any type of service, and indeed the consumer can be any type of, well, not any type, but there are multiple types of services that can be both producers and consumers. If I just a few minutes that I have available to me, if I flip into this week's lab, you can see here from the architecture that I've got an S3 bucket. Okay, the user is uploading images, as it turns out, to an S3 bucket. When that event occurs, that triggers the S3 service to publish or write a message to an SQS to the effect that a new image has been uploaded to the S3 bucket. And this queue then is subsequently, it's being processed by a Lambda. So in the message, in this case, the message will contain details of the bucket, name, and the object, the S3 object key. That's the information that will be contained in the message. And so that means that this Lambda now, when it parses the message, it now has the full address, if you like, of the object. So it could actually, and it does in our case, it can actually grab the image that was uploaded and do some processing of it, although we don't do any processing in this week's lab. In next week's lab, we will take the image and generate a thumbnail version of that image and store that thumbnail in a second bucket. And in the second part of this lab, what am I doing? Oh yeah, the second part is bringing in SNS, which I haven't talked about yet. All right, I'm going to leave it at that for today, and I will publish the template README for the first assignment, the assignment that you're working on right now, and I'll just put a message up on Slack telling you where you can find it. And I've already spoken a little bit about the video, what needs to be in that. I'll pause again for any questions in case you have anything. No? Okay. Thanks for that, and talk to you later.